Now, our graphics library so far only allows us to draw pixels on the screen. In this video, we're going to extend on the graphics library to allow us to draw lines. Now, in order to draw a horizontal line or a vertical line, it's relatively straightforward. Whenever we draw a horizontal line, it's easy enough to pick which pixels we require in order to make the line. But what if the line is diagonal? How do we choose a particular pixel to make the line? So that's what we're going to cover in this video. So let's start off with a grid. Now, this represents the pixelation of our screen. So each of these blocks here is a pixel, and the block can be turned on and also turned off. So how do we represent a line on this screen? So we could just pick a line that we want to draw. So let's say, for example, we want to represent this line here. Now we have to choose which pixels we turn on and off in order to represent this line. So you can see here that if we start down the bottom left, that all of the line here is within this pixel. So we could use a bit of common sense and say, well, we're going to choose this pixel here. But what happens in this instance here, when part of the line is in this pixel and part of the line is in this pixel? Which one do we turn on? Now you could of course turn both of them on, but whenever you do that, you don't get as smooth a line as you would if you were just to turn one of them on. So for the moment, we only want to turn one pixel on, and we have to make a choice. And that's really what the rest of the video is about. How do we choose which pixel whenever there's a conflict? Now let's just go through the rest of these. You can see that the entire line is within this block here, and it's within this block here, and it's also within this block here. So we can choose this one and this one. Now what happens whenever we get to this point here? Again, part of the line is within this block and part of the line is within this block. So again, we have to make a choice. And the final one, all of the line is within this block. Therefore, we're going to choose this end one. So the rest of the video, we will cover an algorithm called Bresenham's algorithm, and it is used in order to make a decision between these conflicting blocks. Now, a common sense way of making a choice between the blocks is simply to work out whether more of the line is in the bottom block or in the top block. If there's more of the line in the bottom block, then we choose the bottom block. If there's more of the line in the top block, then we choose the top block. But we need to make the choice mathematically. So we need to come up with a little bit of mathematics that determines whether most of the line is in the bottom block or in the top block. And this is how we make our choice. So let's see how we're going to do this. We could draw a line from the centre of this pixel to the centre of this pixel. And then we can look at the distance between this pixel here and the point of intersection. And we can look at the distance between this pixel here and the point of intersection. Now, if the distance between here and here is less than the distance between here and here, then we know that most of the line is in the bottom block. And you can see that if we were to, say for example, choose a different line. So let's say we chose a line here. You can see here at this point there is an equality between the both of them. So at that point, if there's an equality, we would need to make a choice between one or another, and we will do that as part of the algorithm. But if we were to move the line up here, you can see the distance between this point and the point on the line is greater than this distance here, so we choose the top one. Whereas if we move down this way, you can see here that the distance between this point and the point on the line is less than the distance between here and here. So therefore we choose the bottom one. So in order to work out what one block we're going to choose, we're going to have to work out these distances and then make a comparison. So let's go ahead with some algebra and we will work out the distance from the point on the line to this point and the point on the line to this point here. Now, one other point I want to make before we go on to the algebra is that we're going to derive Bresenham's algorithm, assuming that the lines that we want to generate have got gradients which are greater than or equal to -1 and less than or equal to 1. Now, the reason for doing that is quite simple. Let's say, for example, we took this line here. Now, this line here has got a gradient of 1. So that as we go along 1 and up 1, along 1 and up 1. So this means that we're able to make a choice between two particular blocks, one block or another block. So when the gradient is less than 1, we're able to make that choice between two blocks. But let's say, for instance, we were to make the gradient greater than 1. So this is the gradient greater than 1 here. Now let's say we move from this block to this block. Now we have to make a choice of the block that we want to choose. But in this instance here, the line runs through this one here, it runs through this one here, and it runs through this one here, and this one. So that means that we wouldn't be making the choice between one block and another block. We would be making the choice between one block, between 4 blocks, and at that point our algorithm would break down. So we're only going to be using algorithm initially for that subset of lines, but it's easy enough to expand and extend it so that it works for all gradients, for all lines. So let's crack on and let's get this done. So let's start on our algebra. I've redrawn a little section of our line out here. So this is a line we want to approximate. And I've put in 4 blocks here. So we know we're going to move from this block into this block, and then we have to make a decision between this block here and this one. But I've also added this one in for completeness. Now, let's say, for example, we call this block in the x direction is going to be the block x subscript k. Now, let's say in the x direction, if we want to go and pick up the next block, we can call that block x subscript k, and we're going to add 1 onto it. So in this instance here, whenever we choose our x blocks, we're always going to just be adding 1 on every time. Now, in the y direction, we're going to have the block and the bottom is going to be called the kth block. So that's going to be y subscript k. And whenever we go up the way, it's going to become y k plus 1. So we can think about this here as the xkth block, or alternatively yk, and we can think of the next block here is going to appear xk plus 1. But whenever we make our decision, we're going to be deciding between the yk block and the yk plus 1 block. So a bit of a mouthful, just take your time and think about that. So it means that if we were to make our decision, what we're going to do is we're going to have the x block, which is going to be next. So we could just call that xn. So in this instance here, n just means next. So the next x block we're going to choose is always going to be the block x k plus 1. Okay, and it will be iterated, so it will be xk plus 1, and then when we're in this block it will be another xk plus 1, xk plus 1, so on and so forth. So that's very simple. But the y block that we're going to choose is going to be the y next block. So we're going to have our y next, and the y next is going to have two possibilities. We're either going to choose the bottom block, in which case we're choosing yk, or we're going to choose the top block, in which case we're choosing yk plus 1. Okay, now another thing to note here is we're going to start off with the equation of this line. So the general equation for a straight line, not the general equation, the equation of the straight line we're going to use is going to be y equals mx plus c. And m is the gradient, so m is equal to the rise, which is delta y, divided by the run, which is delta x. Now I'm not going to go through the mathematics of equations of straight lines. I have another course on basic mathematics which covers all of this in glorious detail, and if you've got any doubts or any questions, you can always go ahead and have a look at that course. So that's the basic setup, and we've named all the things that we're interested in. Apart from one other thing here that we will just add, we're going to have the two distances that we were interested in. So the first distance is from the centre of this block here to the crossover point between the pink and the blue lines. So we can call this distance here d1. And the other distance is from here to this point here. So this is a distance d2. So we're wanting to work out these two distances. So let's move on to the next page, and we will tidy up all of our nomenclature and make it look really nice. We have a lot of algebra in this page, and we will have more algebra on the next page. If you aren't interested in the derivation, then you can always move on to the end of the video and just look at the conclusions. Alternatively, you can look at the next video, which takes the algorithm and it generates the algorithm in our assembly language. So we're going to have our line in blue here, and the line's given by y is equal to mx plus c. The gradient is delta y upon delta x, and we said that we're going to derive this only for fractional gradients. So gradients greater than or equal to -1, less than or equal to 1, and then we will extend it on to all gradients. We said that when we go from this box here, xk to xk, we go to the next box, which is xk plus 1. So the x next is going to be xk plus 1. But when we move over to that box, we're going to have to choose between this one and this one. So in order to choose between these two, we're either going to choose the yk box, which is the bottom one, or the yk plus 1 box, which is the top one. We said we're going to make our decision based on the lengths d1 and d2. So if d1 is shorter than the length d2, then we're going to choose the box at the bottom, which is the yk. So if d1 minus d2 is less than 0, we choose the box yk. If d1 minus d2 is greater than 0, we choose the box yk plus 1. So we can work out the distance d1 and the distance d2. The distance d1 is this height here, so this point, minus this point here. So this point here is simply going to be our value of y for our line, and this point here is going to be our minus y of k. So we can see here we're going to have our point y is going to be our mxk plus 1 plus c, and the minus our yk. Now we can do the same for this distance here. This distance here is going to be this point here minus the value of our y. So we can rewrite this out as going to be the distance here is going to be our yk plus 1 minus our y. So it's this height here, that's the yk plus 1, minus a point here on the line, which is y. We can rewrite this again as yk plus 1, and our value of y again is going to be our mxk plus 1 plus c. Now we can multiply out this line here, right, multiply out the brackets, and we'll get the yk plus 1 minus mxk plus 1 minus c. So those are our two lengths, d1 and d2. So we're interested in the working out the d1 minus d2 because that's how we're going to make our decision. So our d1 minus d2 is going to be this length here minus this here. So we can plug these two in, we get this length and we get this length here. And if we multiply out the brackets and simplify, we're going to be left with this line here, which is 2m xk plus 1 minus 2y of k plus 2c minus 1. Now if we take a look at this equation, the value for c is a constant, so we're not really interested, and the other values that we're interested in are x of k, y of k, but we've also got this term m. Now this term m comes from our original line, and it's the gradient of our original line. But our original line has not been rasterized, so this gradient can have any value, so meaning it's a real number. And we don't want that, because in order to represent real numbers on our computers, we're going to have to use floating points. And the whole point of using this algorithm is we don't need to do that. The algorithm will work with only integers. So we really need to find a way of getting rid of this m. So we can rewrite that m as our delta y upon delta x. So in order to get rid of it, what we could do is we could multiply both lines by a value of delta x. So if we multiply this line here, this side here by delta x, and this side here by delta x, we get the equation below. So this means that once we multiply all this out, we're only going to be left with a delta y here. So the delta y will be a constant value, and you'll see that just in a moment. So that's a nice neat way of getting rid of the floating point number, and that's the reason for running this Bresenham's algorithm. So if we were to multiply this whole thing out, we're going to end up with this line here. Now you'll see here in this line that we mentioned, the only things we're interested in are the things that are going to be change their value of x of k and our y of k. So again, we can take this line here and we can multiply it out again. And when we multiply it out, we get this entire line here. But as I said, the only terms that are multiplying our x of k are this 2 delta y, and the y of k is 2 delta x. This value here is just a constant. This value here is a constant, and this value here is a constant. So whenever we go to make our decisions, It doesn't matter whether we make a decision based on this value here and here, and if we add a constant on or not, it makes no difference to the final outcome. So we can actually get rid of these three terms here at the end. So when we get rid of these three terms, we're left with the decision value. So this thing here is going to become our decision value. But the pk value is going to have to be worked out for each and every individual pixel. So we need to do it for one, and then the next one, and then the next one, and then the next one, and it will change from one pixel to the next. So let's look at that on the next page. So we want to find the next decision variable. So we can call the next decision variable Pn, n for next. So we can say then the next decision variable is going to be our 2 delta y times xn, which is the next x value, minus 2 delta x yn, which is the next y value. Now how do we get the next value? Well, we can look at the difference from the previous value to that next value. So we're going to have our Pn minus Pk. So that's going to be the change in the decision variable for each step over x coordinate. So we can rewrite this then as Pn, which is this equation here, minus our Pk, which is our previous decision variable, which is going to be the equation here, which we've seen on the last page. We can subtract one from another, and we get this equation here. Now, we're going to have two options here. If the difference gives a term which is going to be less than 0, we're going to go through the process here. If the difference gives us a term which is greater than or equal to 0, we go through this process here. So remember, this goes back to the idea of having the two distances d1 and d2. We subtract d2 from d1 and we check and see whether the value is greater than equal to 0 or less than 0. So if the value is less than 0, then we know we're going to be choosing the bottom block. If the value is greater than 0, then the y value is going to increase and we're going to choose the top block. So those are the two options that we have here. So we replace those two options into these equations. So we can take the pk value across. When we take the pk value across, we're going to have the pk plus the 2 delta y. Now the xk was the previous value, so it remains the same. But what's the next value? Well, the next value for x is always going to be xk plus 1. It never changes, that's what it's always going to be. But in this instance here then, what is the next value for y? So the yn. Well, the yn in this instance we've said because the value is less than 0 is going to be just the yk. So we're going to have the yk minus yk, so this disappears. And when we simplify this out, we're going to have our Pn value is going to be pk plus 2 delta y. So now finally what we can do is, rather than calling the value for the next decision variable n, we'll actually call it pk plus 1. Okay, so we're going to have the value for the next decision variable pk plus 1 is equal to the old decision variable pk plus 2 delta y. So that's in this instance here when the value here is less than 0. What if it's greater than or equal to 0? So we go through the same process here. So in this instance here, the value for our yk will now be yk plus 1. So whenever we multiply out the brackets, we're going to get our pk plus 2 delta y minus 2 delta x. And again, what we can do is, rather than call it Pn for next, we'll just call it pk plus 1. So the pk plus 1 is going to be equal to pk plus 2 delta y minus 2 delta x. So you can see it's different depending on the whether this value is less than 0 or greater than or equal. to 0. So it's a bit of a mouthful that, but take your time and break it down into little blocks and understand each of the blocks. The actual algebra is not necessarily that important as long as you get it right. What matters is that you understand why you do the algebra and why you go from one position to another position. So finally, we're going to have to work out one other thing, and that is the initial value for pk. So let's do that here. So we worked out in the previous page that the value for our pk, so let's call this in this instance our first value, and we'll call it p1, is going to be given by this equation here. So again, we derived that in the previous page. Now what we're going to do is take the equation of a straight line, y is equal to mx plus c, and we can rewrite that. So the value, if we rearrange this for c, is going to be y1 minus, and we can make the gradient m is going to be delta y upon delta x. So we can take this value for c and we can place it into this equation here. So whenever we place it into this equation here, we're going to get this equation. Now I'm not going to talk through the equations, you can go through yourself and with a piece of paper and check them. So we've replaced this c here with this equation here. Now whenever we multiply it out, we're going to get this here. And these terms here are going to cancel. You can see this term here will cancel with this term here, and this term will cancel with this term. And it's going to give us the value of 2 delta y minus delta x. So that's going to give us our pk value. So that's us almost finished. We'll finish it off on the next page. So here is the algorithm. We're wanting to draw a line y is equal to mx plus c, and we've got this xk because we're telling it we want to draw a line a pixel at a time. So xk plus 1 is going to be the next pixel. Now in order to do this, we have to make a decision between 2 pixels, and we make the decision here, and the first value for our decision is going to be given by 2 delta y minus delta x. Now we get our delta y and our delta x by taking the y coordinates of the beginning and the end pixel from one another, and the x coordinates from the beginning and the end pixel from one another. Now if the value here is less than 0, then we get the next decision algorithm from pk plus 2 delta y. The xk plus 1 becomes xk plus 1, so we just go on to the next one, and the yk plus 1 is the same as the previous yk. Now if this value for our decision algorithm, our decision, is greater than or equal to 0, we go through this process here. So the next value for our decision, pk plus 1, is given by pk plus 2 delta y minus 2 delta x, and the value for our xk plus 1 again is going to be the same. It's going to be xk plus 1, and the yk plus 1 now is going to be yk plus 1, so we choose the next one up. Now that's a bit of gobbledygook. It's best looked at using an example. So what we will do in the next video is we will actually go through the example which we looked at from the start of our derivation. So that's this line here. So it's going to be going from this point here, 1.5, 0.5, along to 8.5, and that's going to be 3.5. So we will put those values into our Bresenham's algorithm, and we'll check and make sure that we actually get these blocks lit up and it does follow this pattern. And we'll do that in the next video. So thank you for listening to this video. I'll get you on the next video. Goodbye.